It's a lot more sexy to talk about, oh, bad pharma doing this bad stuff, and oh, look at those bad scientists committing all this fraud. And yes, that sort of thing does happen, and there is scientific misconduct, but a lot of the misconduct, a lot of the problems with reproducibility actually stem from unintentional errors. They stem from poor experimental design, and sometimes that kind of happens because there's not adequate training of the people that are going to be conducting the experiments. So you go from undergrad or some sort of position where they're giving you this kind of recipe. Okay, follow this recipe step by step, set up this and this well, this and this well, this and this well. And you do it and you're learning the technique. Great. You can interpret the results. Great. But now you go and your boss says, okay, now scale this up. Or maybe you have to actually design experiments to test a hypothesis that you have towards your grad school thesis. And now you have to actually set up these experiments, and you don't know how to set up these experiments. You just know how to follow a protocol. When you are setting up experiments, how you set them up really matters. Because if you set them up incorrectly, you can be introducing systematic errors, so problems that are kind of technique-wise that bias the results, and they can consistently bias the results in specific ways. And so some of the main ones you'll see are batch effects and edge effects, as well as other position effects and other differences in techniques, standard curve application, these sorts of things. It's important to try to prevent them from happening in the first place, and then be able to detect them if they do happen. And sometimes you can correct for them after the fact, but a lot of the times you can't, and therefore it's really important that you set up your experiment to have the biggest chance of success. When we talk about batch effects, that's where you kind of have differences that are really kind of just artifacts. From the same sample, you might get different results if that sample was processed on different days or in different batches, even on the same day. This can happen because of things like differences in the temperature. If you're working with enzymes, temperature is like crucial. You can have totally different temperatures on different days, and that could totally influence your enzymatic rate. That happened to me over the summer when it was really hot one day, and I'm like, why is my enzyme so much more active? It's because room temperature on that day was a lot higher than room temperature on another day. And so temperature control whenever possible is great, but if you don't have that, then be very cautious with interpreting results that were processed on different days. In addition to batch effects kind of being caused by differences in the environment, so things like temperature and humidity, differences in the equipment from day to day, there are also differences when different people perform the same experiment. And so differences in technique, differences in pipet angle, all of these things can influence the results of the experiment. Whatever you do, like when we're going to talk about a bunch of different problems, the best thing is always to process samples that you want to compare to one another in the same batch, in the same test, measure their concentrations with the same technique on the same day, in the same, like side by side, all these things. The more side by side you can be in these things, the better your chances of having a real true comparison that you can actually replicate and that you can rely on. To help you see whether their batch effects are occurring, you could run your samples on multiple days, as well as you should always have some sort of control sample that you run on different days with each batch that is kind of the same thing, so that you can then see, okay, well, I should be getting the same result with these, and if not, maybe there is some sort of correction I can do after the fact, but that just depends on the technique and things. What you can do, however, is in each of your batches, you want to kind of rotate where you put different samples. And so this gets to things called edge effects, as well as other position effects. So edge effects, this relates mostly to when you're doing things in plates. So those plates with like lots of different wells. On the edges of those wells, you're going to have more evaporation than in the center. And when you have things evaporate, then you can have kind of the concentration of things is going to increase in the cells. And you can also have other sorts of problems if the reaction, say, is heat sensitive. There are different types of plates that try to account for this, as well as differences in the equipment that kind of holds the plates. So there is some sorts of things that try to get around this, but the best thing that you can do is if you don't need to use all of the wells and things, put your stuff in the center. And if you do, then you kind of, or even if you don't, you want to always be rotating your samples. Because not only can there be edge effects, but there could also be other position effects where differences in plates in the plate just kind of have differences in heating due to how the holder is setting them up or things. Speaking of setting up, you're often going to be setting up these experiments using something like a multi-channel pipette where you've got a bunch of different channels. Now, ideally, all those channels pull up the exact same amount of liquid every time, and so it's super duper consistent. In reality, sometimes one of those channels might be a bit off in terms of like its calibration or how tightly it grips the tip. And so you might consistently find that, say, the center channel has a lower volume than the outer channels. And if you set up your experiment so that you have the same sample in that position in all of your different replicates, then you're going to have a kind of bias at that one place, and that's totally just an artifact of your technique. Also with multi-channel pipettes, if you are kind of at an angle when you're picking up the tips or when you're aspirating, that could influence the actual amount of liquid in the different tips. And so rotating your samples is the best way to kind of account for this, and then also having good technique when you're pipetting in the first place. And so you want to be rotating your samples and things. And this can be a bit of a hassle. And so all of these things are going to take significant amounts of time, effort, and money. And so it's not always practical to do all of these really tight controls and rotating samples and doing everything in high replicates and replicates of your dilutions, not just technical replicates from the same dilution, but actual different dilutions, preferably from different samples and all these things. But that's really what you need if you want to have super rigorous results. In the scouting phase, however, when you're just trying to learn an experiment, figure out if an experiment might work for you, then often we're going to be kind of more lax in how we set up these experiments. It's always important to include some controls, but not as many controls, and you're typically not doing as many replicates and things. And this is okay when you're just trying to start out and see whether the experiment might be something that would be appropriate for you. Learn the technique, try to troubleshoot, and often you're going to be doing this with kind of just generic proteins, something like BSA or lysozyme, so you don't waste your precious samples. And then once you've got the technique figured out, now you can go ahead and use it on your samples. And so a lot of the times we're really eager to get results, but if those results aren't things that we can trust, we don't want to then go report those results until we're able to then verify these results using a more rigorously set up experiment. An experiment, when we are rotating our samples, we have lots of replicates that aren't just technical replicates, and so they're not just us taking the same sample and putting it into multiple wells. I mean, those can only account for so much of the difference, not for the actual differences in how you prepared the samples, only the differences in how you pipette them into the well and things. You want to have actually as many kind of real replicates as possible to account for differences in the sample. In most cases, the best thing that you can do is test the sample multiple times in multiple batches next to, side by side with, the thing that you actually want to compare them to. You want to make sure that those samples are processed the same way, that they are measured the same way, that their concentrations are determined the same way. This is a really common problem in biochemistry, especially when it deals with proteins. Protein concentration is ridiculously hard to measure, and so there are different methods like Bradford assay and BCA and UV280, and all of these methods can give you vastly different results. This comes down to biases in the experimental technique that you kind of can't control. Things like the dye binding to certain amino acid residues more than other amino acids. You often compare to a standard curve, but that standard curve is then subject to the same biases. So if you use BSA versus BCG, you'll get different standard curves. Let alone the fitting of those curves could give you different results when you're then trying to apply that equation that you use to fit the curve. And so the exact same protein, if you measured it with these different methods, or even if you measured it with the same assay, but using a slightly different standard curve application, then you could actually get different results. And so you want to take your samples and measure them concentrations side by side. Now, this means that if you got rid of all your sample, you're kind of screwed. What you want to do is you always want to save some of your sample whenever possible so that you can do repeat kind of experiments in the future. You can measure the concentration side by side with your newer samples. So say you do an old enzyme preparation and now you have a new enzyme preparation. You want to make sure that you test the new one against the old one so that you can accurately compare the results to one another. Or else you might have these totally different results that really aren't different. They're just differences in the technique. Speaking of differences, when scientists talk about significance, this is often in the sense of statistical significance, not real life significance. And so say your hair grows 0.1 inch longer in people that take this certain drug compared to people who take a placebo. Well, maybe that result is statistically significant. It's likely that it's not caused by chance, but is it really significant in the fact that it would have significance in the lives of the people? No. And so you need to be careful with interpreting things when they say significant, and also know that there are problems with the statistical significance test, and that gets into a whole nother level of what do we say is a difference, but I'm not going to go into the data analysis side of things. That is a whole nother story, and that's actually a side of the story that's covered a lot more. And so often you're going to be hearing about people trying to hack the statistics and p-hacking and all of these things, cherry picking, doing tons and tons of comparisons, and then some of these are just by chance going to be significant, and they're like, oh, we found this finding. And they're not correcting for the fact that they did tons and tons of experiments. And then you just hear, oh, this is a significant finding, and it's not really significant. And then they do it again, and it's not even found. But I'm not going to go into that because that's gone into all over the place and things, and that's not my area of expertise. But in order to actually have a chance to have good results, you actually have to set up your experiment correctly. And again, when you're setting up your experiment correctly, you want to make sure you have good technique. You want to make sure that you are looking for batch effects, differences between the same kind of samples on different days, in different batches, done by different people, all these things. You want to be rotating your samples in your plate. Avoid the edges whenever possible. Rotate your samples around in terms of where they are in the plate, where they are from side to side. I know it's a pain because often it's easy to just go and use your multi-channel or whatever and have the same samples in the same order, and then you're setting up your analysis and you have the same thing in the same order. But that then means you have the same bias in the same places in each sample, and basically, so some samples might have one bias that the other samples don't have, and then this can totally influence your results. So at least when you're replicating on a different day, be sure that the sample order is different and things. And again, I know that this is a hassle. This can be a big cost and time and effort problem, but when you're trying to get those results for publication, for actual designing future experiments, high cost experiments and things then it's really crucial to have those. When you're doing the scouting out experiments, yes, you can be a little more lax, but when it comes to those results that you're then going to present to people, that you're then going to base your clinical program off of, it's really important that this data is reliable. And scientists in pharma and scientists in clinical development and all these places are relying on basic researchers like myself, in order to do the research correctly and not just give them spurious results, because the data stuff that they do is only as good as the science that we do. And even the machine learning and all of these things, they're relying on experimental data. Experimental data needs to be collected appropriately and accurately in order to have a chance of using all of these big machine learning things and all that to give us accurate results. And then those results from the machine learning tools are then often followed up with this at the bench research. And so it's important that this at the bench research is done correctly. Whatever you do, keep good notes. In best practice, you keep things like batch numbers of your reagents, so that if there are differences in the reagents that could be causing batch effects, you want to at least have your sample prep dates. Again, save some of each of your samples so that you can use it at a later date and do side-by-side comparisons. All of these things, thinking ahead and being critical of your own results, not just other people's results, is going to be really crucial. Food for thought, look back in anger, what clinical studies tell us about preclinical work by T. Hartung. Rigor mortis, how sloppy science creates worthless cures, crushes hope, and wastes billions by Richard Harris. And unreliable, bias, fraud, and the reproducibility crisis in biomedical research by Shaba Sabo. And again, I hope this doesn't scare you off from science. It just helps you be a better scientist.